8.3 Magnetic force on a current carrying conductor. How does a speaker work? Inside a speaker is an electromagnet as well as a permanent magnet. The magnetic field of the permanent magnet exerts a force on the current in the coil of the electromagnet. The speaker uses this force to produce sound waves. Simply put, a speaker works because a current carrying conductor experiences a force in a magnetic field. There's an equation that governs the force on a wire, and it is force on a wire is equal to current times the length of the wire times the magnetic field strength times the angle between the magnetic field and the current. Okay, the diagram that is given in the textbook attempts to illustrate how to use the right-hand rule to determine the direction of the force on a wire. But I think that the diagram is pretty confusing. So instead, I photographed my hand. Please, as I zoom in, I apologize. I probably should have had a proper manicure or put some moisturizer on, but if we can get past that, we're going to use our thumb on our right hand to indicate the direction of the current. And again, this is the direction of conventional current. Our fingers will point in the direction of the magnetic field. So you can see from this diagram that my fingers are pointing out of the page. And to indicate that, we use dots. Those dots show that the magnetic field lines are coming directly out of the page. Just an aside, just to let you know, this is the magnetic field. So it would be out of the page. If it were going into the page, this is totally an aside. Instead of using dots, we would use X's. So an X would denote that the field is going into the page. Okay, it's a bit of an aside. In fact, I'm going to erase it so you don't get distracted. If the electric field represented by your fingers is coming out of the page and the current represented by your thumb is perpendicular to the field, then that means that the electric force on the wire, the magnetic force on the wire rather, will be from the palm of your hand. And this is the force on the wire. And it's coming as if it's from your palm. So please use your right hand, practice this rule, and see if you can visualize it. I think that this photograph does a way better job of the diagram in the textbook. Let's try a sample problem. Let's calculate the magnitude of the magnetic force on a wire using a uniform magnetic field. A piece of wire 45.2 centimeters long has a current of 12 amps. The wire moves through a uniform magnetic field with a strength of 0.30 Tesla. Calculate the magnitude of the magnetic force on the wire when the angle between the magnetic field and the wire is A, 0 degrees, B, 45 degrees, and C, 90 degrees. Let's start with part A, where theta equals 0 degrees. We know the force on the wire is equal to ILB sine theta. The current is 12 amps. The length is 45.2 centimeters. That's 0.452 meters. We know the magnetic field strength is 0.30 Tesla. And in this case, the angle is 0. If we punch this in, the sine of 0 is 0. So our force on our wire will be 0 newtons. In part B, theta is equal to 45 degrees. So we're going to sub in the same equation. We're dealing with a current of 12 amps, the same length of wire, 0.452 meters, magnetic field, 0.30 Tesla. In this case, we're looking at the sine of 45 degrees. If we punch this into our calculator using this new angle, we'll get a force of 1.2 newtons. Let's do the same in part C, this time using the angle theta equals 90 degrees. So 12 amps, 0.452 meters, 0.30 Tesla times the sine of 90. If you punch this in, you will get 1.6 newtons. So the magnitude of the force on the wire is 0 when theta is 0, 1.2 when theta is 45 degrees, and 1.6 when theta is 90 degrees. Let's try sample problem number 2. In sample problem number 2, we're determining the magnetic force on a segment of a current-carrying wire in the Earth's magnetic field. 2 electric poles support a current-carrying wire. The mass of a 2.5 meter segment of the wire is 0.44 kilograms. A 15 amp current travels through the wire. The conventional current is oriented due east, horizontal to the Earth's surface, and the strength of the Earth's magnetic field at that particular location is 57 microtesla and is oriented due north, horizontal to the Earth's surface. I've drawn the right-hand rule for the force on a wire in a magnetic field, and we line up our straight fingers with the magnetic field, our thumb with the direction of the conventional current. So from our palm of our hand, that's where we will get the force on the wire, the direction of it. If we want to determine the magnitude of the force on the wire, we'll use our equation, ILB sine theta. The current is 15 amps. The length is 2.5 meters. It said that the magnetic field has a magnitude of 57 microtesla, which is 57 micro means 10 to the power of negative 6 Tesla. And we know that since the magnetic field is north and the current is east, then theta is 90 degrees. If we punch this into our calculator, we'll end up with a force of 2 times 10 to the power of negative 3 newtons. Therefore, the magnitude of the magnetic force on the 2.5 meter segment of wire is 2.1 times 10 to the power of negative 3 newtons, and the force is directed upward. In part B, they want us to calculate the gravitational force of the 2.5 meter segment of wire. So the gravitational force is equal to the mass of the wire times the gravitational field intensity. We know the mass of the wire is 0.44 kilograms, and G is 9.8 newtons per kilogram. So the gravitational force on the wire is 4.3 newtons. Therefore, the gravitational force on the 2.5 segment meter of wire is 4.3 newtons. I want you to do a few things for homework. The first is to attempt practice problems on page 395 and review questions on page 396. Then I want you to read some of the applications of the force on a wire in a magnetic field and use this to explain how loudspeakers and electromagnetic pumps work. Good luck.